Okay, I'll put an example up for you guys to work through. Okay, this is actually will come from our text here, and so this is this says so Samuel Morse, inventor of Morse code, hypothesized, said, made a claim that that the letter E is the most common letter. Okay. It's most common in English. And it accounts for 12% of the letters used. Okay. We looked at a page of text, at a quote random page of text. There were 876 letters. Letters in the text. And 118 of them are E's. Okay? So our P hat would be 118 divided by 876, and we have 0.1347. Okay, we'll say if Morse's claim that 12% of letters are E's is true, okay, what is the probability that a random sample of 876 letters ends up with 0.1347 or more E's? Okay, so this is the question, and I'll give you guys a few minutes to work on this. You can apply the central limit theorem, so you don't have to worry about checking for the conditions in this case. Okay, and you want to use the central limit theorem, so you're going to have to find out your mean and your standard deviation, and use that as kind of the normal model to answer this question. What's the probability of getting 0.1347 or 47% E's or more? Okay, 0.1347 or more E's. Okay, so I'll give you guys a few minutes to work through this. I'll pause the video if you're watching on YouTube, so you can have a few minutes to work through this problem yourself. Okay, so as you guys are working, you should see that P is the proportion in the English language, that's E. Okay, so this is the proportion of E's. And our N is our sample size, which is 876. Okay, so at this point, you've got to figure out your mean and your standard deviation. So from the central limit theorem, so earlier, if you flip back earlier in your notes from today, you should see that N times P is your mean mu, and your standard deviation is going to be p times 1 minus p divided by n. Okay? So you've got p, you've got n, you should be able to get these. Okay? So go ahead and keep working, and once you have this, you should be able to use your normal model to answer your questions. Okay, so I know some of you guys are working hard on this, and that's great. All right, let's go through. Let's go through. Okay, so as we're reading this, okay, so it says if Morse's claim that 12% of the letters are E's is true, so that means what we're saying is that in our population, P is equal to 0.12, so we've written this down already. And we've taken a random sample of 876 letters, okay? So what we're expecting, oh, I don't know why I wrote mu, I'm sorry. This should just be P, I don't know why I wrote N times P, I apologize for that. Mu is just P, and our standard deviation is this, okay? So our mean is gonna be 0.12, and our standard deviation is going to be the square root of 0.12 times 1 minus 0.12 divided by 876. Okay? Is this okay so far? I apologize for a mistake earlier here. Do we at least have these numbers plugged into here? Okay, so on the calculator, we can do this in one step here, okay? Now, you might want to break this up, but so maybe you did 1 minus 0.12 is 0.88, okay? So you can do 0.12 times 0.88 divided by 876. I'm going to hit enter here, okay? And we get 0.0001205 something something something, okay? We have to remember we still have to take the square root, okay? And so if you have one of these style calculators, you can just hit the square root button, and then rather than having to retype all of this in, you can just hit the answer button, okay? And that's going to plug in this result into that square root, okay? And then I hit enter, and the result is 0.010979, okay? So that's my standard deviation, 0.010979. Okay. So if you want to see me do that again, I can even just do 0.12 times and then parentheses 1 minus 0.12 close parentheses divided by 876. I hit enter, and then I hit the square root, answer. I get that number. Okay. And I'm going to actually leave this in here because this is going to come in handy when I calculate my z-score, okay? So let's say I want to get my z-score. So right now what I have is I have a normal distribution with mean 0.12 and standard deviation 0.010979 or something like that, okay? And essentially now I'm looking at 0.1347. So z is equal to x minus the mean divided by standard deviation. I'm going to have 0.1347 minus 0.12 divided by 0.010979. Is this okay? So I'm just plugging in the values. I want to, if I draw a picture, I have 12% in the middle. I'm going off to 1347, and I want to shade the area to the right and ask how much is shaded here. Okay, so this might be helpful for you. This is how I do my math on the calculator to save me time. I type in parentheses 0.1347 minus 0.12 close parentheses. So essentially I'm just putting in the numerator in parentheses so that the calculator does this first. And then I'm going to hit divide, and then rather than having to type in 0.010979, I can see all of those numbers are already there. I'm going to just hit the answer key and hit equals. And I get a z-score of 1.3388, so 1.34. A z-score is 1.34. Should I do that again? Okay. So again, so in my calculator, I have the results of the previous calculation, which is my standard deviation of 0.010979. Okay. I want to get my z-score, so I'm going to hit parentheses 0.1347 minus 0.12, close parentheses. Okay, and that's just the numerator of this part. I have that right there. I'm going to hit divide, and then I'm going to plug in. I could type in 0.010979, whatever. I can type in that full number if I want to, but I don't have to because I have an answer button on my calculator. Okay. So if you have a scientific calculator, whether it's Texas Instruments or Casio or whatever brand, a lot of them have answer buttons. You might have to hunt around for it, but I find it to be a great button to have on a calculator. Okay, and then I hit equals and I get 1.3388. Okay, so that rounds off to 1.34. Okay, I'm not done because I have to look this up and find the area to the right. So I'm going to look up 1.34 in the z table. 1.301234 is 0.9099. Okay, so the area to the left of z equal to 1.34 is equal to 0.9099. So that means the area to the right is going to be 1 minus. So at this point now I have to do 1 minus 0.9099, 0.0901. Okay, so I get 0.0901. So we have about a 9% chance that a random sample ends up being 1347% E's or more. Okay, so about 9%. Is this satisfactory? Yes, question.
Can you just repeat the very last part?
From 0.9099? Or from my z-score?
So the 0.0901,
Yes.
what that number represents?
This is the answer to our question. Our question was if the claim that 12% of letters are E is true, what's the probability that a random sample of 876 letters end up with 13, or basically 13.5% E? Okay, so just imagine instead of the vat of candy, we've got a vat of letters. Okay, these letters represent the English language. Okay, so you know, E's will show up a lot, X's and Z's and Q's not so much. Okay, we're going to pick out 876 letters out of this giant vat. Okay, now if 12% of the letters in that vat are E's, I should get something around 12% E's when I pick 876. Maybe I get more, maybe I get less. The question is, what's the probability that I get basically 13.5% or 0.1347% E in this, you know, metaphysical bucket of letters, okay? Well, if 12% of the letters are E, this is going to happen 9% of the time, okay? Does that make sense? Yes?
So in a sense, it's a percentage of a percentage.
It's the probability associated with a percentage, okay? So it's not, we shouldn't think of it as a percentage of a percentage. We're saying this bucket has certain proportions in it. This bucket is 12% E's. I'm asking what's the probability associated with getting a certain percentage of E's, okay? So I guess if you want to say it's a percentage of a percentage associated with a percentage, that's okay. But I think it's better to think of it as a probability associated with getting a certain percentage, okay? Okay, I hope this makes sense. Um, you have some sample problems on a practice quiz that kind of work through this also. Okay, you know, some of you were asking for kind of maybe help in studying and things like that. What I recommend is working through the homework problems before you work through the sample quiz. Okay, because I think if you go straight to the practice quiz before you do the homework, it's easy to kind of get accustomed to the exact questions that show up in the practice quiz, and I think they are quite representative of the actual quizzes, but you lose an opportunity to practice or test yourself, and I think it's good to use the homework to make sure you've learned the concepts. Once you've learned the concepts, then you can test yourself with a practice quiz. Make sure you truly understand the way you should, okay? And I think it's good to kind of test yourself under timed test-like conditions where you don't have the book in front of you and things like that. Time yourself, see if, and work the answers out until you get a final answer. Like, pick the answer. Don't just do half of your work and say, I'm going to look for the answer. Just actually pick your answer and then check. And then see, you know, maybe I made a mistake. Maybe I forgot to subtract from 1, or maybe I subtracted from 1 when I wasn't supposed to. Maybe I circled the z-score rather than the percentage or probability. I think these things come to light when you put yourself under test-like conditions. But you've got to make sure you understand the material first, and that's what the homework is for. All right, let's keep working here, okay? All right, so what the central limit theorem establishes, okay? Establishes that a random p hat comes from a normal distribution. Where the mean is p. Okay. So again, if you just, you know, it's silly to think of things this way, but you just think of, you have this bucket where you've got a certain proportion is something, right? So if we're selecting people, you know, and we want to know what percentage of people support whatever, this candidate, okay? You can just imagine we've got a pretend bucket of people, and we're going to randomly pick people out of this bucket, and we're going to count how many of them support a certain candidate, okay? It's much in the same way that we're drawing the candy pieces out of the bucket, okay? And so if we know that in the bucket we have exactly 60% of this thing, when you take random samples, we're expecting something around 60%, okay? And the central limit theorem says, yes, you can expect something around 60%, and in fact, the way they're distributed is via the normal distribution, which means things in the middle are quite common, right? 68% within 1 standard deviation, 95% within 2 standard deviations, almost 100% within 3 standard deviations. The central limit theorem says, yes, whenever you draw a random sample out of the bucket, the proportion you get is going to be similar to the actual proportion in the bucket, but not necessarily exactly that, okay? So that's what we've established so far, and so we're going to apply kind of the reverse of that. Now I don't know what exists in the bucket, okay? I don't know that the bucket is exactly 30% orange. I don't know this. But if I draw a random sample of candies out of the bucket, and I see that, let's say, 42% of these candies are yellow, what percentage of the bucket is yellow? That's the question I want to ask now. If my sample is 42% yellow, does that mean the bucket is 42% yellow? Well, not necessarily, but it means the bucket is probably something close to 42% yellow, okay? And that's the concept that we're approaching with confidence intervals, okay? So confidence intervals apply our understanding of sampling distributions. Okay. This time we don't know what exists in the population. Okay, we do not know, so we'll stick with candy pieces. Okay, so we do not know what percentage of candies in the bucket are yellow this time. Okay, but we're going to oh, my battery's just died. Okay, but we do know, but we do observe a sample. Okay, so we don't know the percentage of candies in the bucket, what percentage of candies in the bucket are yellow. Okay, but maybe we take a sample and see that 42% of our sample is yellow. Okay. What does this say about the bucket? Okay, this is the question that confidence intervals try to apply, and the answer is, well, the bucket is probably something around 42% yellow. But this sample that I have, maybe it has too many yellows. Maybe it doesn't have enough. We don't know, okay? If we surveyed people, just like in the election when a new poll gets published and they say this is the percentage that's going to vote for whoever, okay? We don't know if that number is too high or too low, okay? And that's why, different organizations, they publish different polls and they're all over the place, okay? We don't know if a certain number is too high or if it's too low. So, but right now, our best guess, 42%. So when we talk about a confidence interval, we're going to say, okay, well, I'm thinking the population, the bucket, is probably around 42% yellow, give or take 5% or something like that, okay? And we give ourselves what we call the margin of error. So, those polls do the same thing. We say, yeah, I think the bucket is 42% yellow, give or take 5%, okay? And so effectively that means the bucket could be anywhere from 37% yellow to 47% yellow, okay? Or maybe you're not quite sure and you say, okay, well, maybe I should play it safe. Give or take 10% or something like that, okay? If you've taken a small sample, you're probably less confident, so you have to give yourself a lot of margin of error. So if your number 42% is based on a small sample, your margin of error maybe have to be 10% or even bigger, okay? If you've taken a giant sample, you can probably use a small margin of error because that number 42% is probably a pretty good estimate. So you can say maybe a margin of error of only 2% or something like that. Okay? So what does this say about the bucket? Okay, well, you know, right now, 42% is our, quote, best guess. Okay? Okay? We will give ourselves margin of error. And say something like okay, you know, I think the bucket is, you know, 42% yellow, give or take 5% or something like that. Okay, this 5%, this is our margin of error. Okay, that this margin of error, you know, I kind of just made it up on the fly, but there's actual formulas that we use to give us an exact value for the margin of error that we should use. But this is kind of the idea of a confidence interval. We'll look at a sample, and right now, whatever we see in the sample is our current best guess, which makes sense, right? Because, you know, assuming that it's a random sample, we don't know if by random chance we got too many of one thing or too little of another. So we just say, okay, well, right now my best guess is what I saw in the sample, 42%. Okay, but I got to give myself some room for error. So I'll say plus or minus, or give or take 5%, give or take 8%, whatever it might be. Okay, and so we'll go through the process of defining that margin of error. Okay, is this concept okay? Okay, so I'll put up the formula / equation for a confidence interval. Okay. All right, so we say, you know, a confidence interval for P. This is the population proportion based on a sample P hat. Is okay, it's going to be P hat plus or minus this is basically give or take. Okay, we read this as plus or minus or give or take we have what we call a Z star times the square root of P hat times 1 minus P hat over N. Okay? This looks very similar to the standard deviation when we were dealing with sampling distributions, but we have P hats and not P's. Okay? So notice the P hats. Okay? I'm going to label these other pieces. Z star is called the critical value. And this quantity, this is called the standard error. Okay. And then when you take the critical value times the standard error together, the Z star times the square root, I'm just going to write Z star times the standard error. This is known as the margin of error. The entire part that is plus or minus, this is the margin of error. So that's this is the value that gets published, you know, in survey results and things like that. Okay, p hat, this would be our sample proportion. Okay, it also serves as the center of the interval. All right, so let's try this out. We'll see what we can say. Okay. Oh, I'm sorry. All right. So, before we try it out, I have to talk about this critical value z star. Okay. If you want to be very confident that your resulting interval kind of gets the true value of p, you've got to make a wide interval, right? If you're really not sure and you kind of want to boost how sure you are, you just make the interval wide, right? You say, well, I think it's 42%, give or take 30% or something like that, okay? Then you can be pretty confident that in between 12% and 72%, you've probably got the right answer somewhere in there, okay? But it's silly to have something so wide. But if you're willing to be less confident, you can get away with a narrow interval, okay? So our choice of z depends on our confidence level, okay? So I'm going to give you 4 values of z that you have to either memorize or make sure you write on a note card, okay? So next week when you do your quiz, make sure you have these 4 values of z written, okay? Don't tell me that I did not warn you, okay? So 4 values of z star to memorize or make sure is on the card. Okay? And this is, you know, for the confidence level, if the confidence is, if you want to be 99% confident, then z is 2.58. 2.58. For 95% confident, use z is 1.96. For 90% confidence, use z equal to 1.645. And for 80% confidence, z is 1.28. Okay, these are the 4 values of z that either you need to memorize or make sure is on your card. These, if you were to look up z equal to 1.28 in your table, you would see that it's associated with 90%. Okay, and that the reason why it's going with 80% is because I'll just draw the little picture here. You don't have to draw this in your notes, okay? We're gonna have 10% over here, 10% over here, so you're gonna have 80% in the middle. But the table always gives you the area to the left, so it's gonna report the 80% plus this left-hand 10%, and that's why it will say 90% in the table, but you don't have to worry about that. Let me just delete that before some of you guys get confused, but some of you saw that and it made sense. Okay. All right, so now let's, so I'll copy these values onto the next slide, and we will we'll try this out here. So these are your 4 values. I'll just do that, that's fine. Okay, and then we have p hat plus or minus z star times the square root of p hat times 1 minus p hat over n. Okay, so we're going to say we want to know what percent of people, I don't know, we'll say people in the USA what percentage of people in the USA, we'll say, drive a truck? Okay, so we surveyed 220 random people. And we'll say 78 of them drive trucks. It's probably higher than that. Whatever, okay. All right, make a confidence interval. With, we'll say 95% confidence level. Make a confidence interval for the proportion of all people in the USA that drive trucks. Okay, so the approach with any of these things is before you start trying to plug numbers into some formula, go through the problem and see if you can identify the values you need. Make sure you can identify what your p hat is, what your z is, what your n is. Okay, there might be some computations involved. Okay, so go ahead and try that out. All right, let's try this out. Okay, so our population is all the people in the USA, and the parameter that we're interested in is what percentage of them drive trucks. Okay, we surveyed 220 random people, I guess random people from the USA. 78 of them drive trucks, so we're going to say p hat 78 divided by 220. I think most of you guys got this as I was walking around. 0.3545. This is our proportion in the sample that drive trucks. Okay, so when we surveyed 220 people, 35 of them drove trucks. So if we surveyed everyone in the United States, what percentage of them drive trucks? Okay, well, probably something around 35%, maybe more, maybe less, we don't know, okay? So let's, what we've got to do is we got to figure out the give or take amount, okay? So because it says 95%, we know that the z star we're going to use is going to be what? 1.96, okay? And what is the n that we're going to use? It's our sample size, 220. Okay, so I'm going to just plug in all of these values into this equation here. I got 0.3545 plus or minus z star 1.96 times the square root of 0.3545 times 1 minus 0.3545 divided by 220. Okay? So I'm going to calculate what's inside my square root. So this is going to turn into 0.3545 plus or minus 1.96 times, I'm going to calculate this part. So I've got 0.3545 right here. I'm going to do times, parentheses, 1 minus my answer. I use the answer key because I'm lazy. I don't feel like typing in a bunch of numbers. That's why I do it, okay? So, you know, I've done my calculation, 78 divided by 220, so I've got 0.3545. So anytime I hit answer, I know 0.3545 is going to get plugged in. So I got answer times 1 minus the answer. And I'm going to divide that by 220. I hit equals, and I get this number, and I'm going to take the square root of this number. Square root of 0.00104, square root of that is 0.03225. So I got 0.3545 plus or minus 1.96 times 0.03225. Okay? Is that okay? So far so good? All right, I'm going to multiply this number by 1.96. So I'm just doing answer times 0.03, again, because I don't feel like typing these numbers out. I hit times 1.96 and I hit equals, and I get 0.0632. Okay, so here I've got 0.3545 plus or minus 0.0632. Is that okay?
Can we just go back a little bit?
Sure, where should I go back to?
Just before the 3545 plus or minus 0.6.
So all I've done is done 1.96 times 0.03225. These two numbers combine. If I multiply 1.96 times 0.03225, I get 0.0632. Okay? So all I've done is just copied each of my steps here. All right? So now I have 0.3545 plus 0.0632, and I have 0.3545 minus 0.0632. Okay? Let me just pause here and just basically say, right now, my answer to this question. Okay? We want to know what percentage of people in the USA drive a truck. My answer right now is about 35%, 35.45%, give or take 6%. Give or take 6.32% is what I'm saying, okay? So I've got 0.3545. So, you know, what percentage of people in the US drive trucks? Around 35.5%, give or take 6%. That's essentially what I'm saying right now, okay? It looks a little bit more complicated because I've got decimals here, but it's not. What percentage of people drive trucks? 35%, give or take 6%. That's basically what I'm saying. Yes?
For the Z, where did the 1.96?
And 1.96, I said there were 4 numbers that you're going to have to memorize or write down. And it just says if you want 95% confidence, that Z that you're going to use is 1.96. Okay? It's just the rule of making these confidence intervals. They're based on the normal distribution, but you know this is what we got. Okay, so what I'm going to do is I'm going to do the plus operation first. So I'm going to do 0.3545 plus 0.0632. Okay, so basically when I say what percentage of people drive trucks? About 35%, give or take 6%. Well, if you give 6%, you're going to end up at 41.77%. So this equals to 0.4177. Okay, and I can just hit the back button, all right, and hit delete minus. So this is 0.3545 minus 0.0632. So if I take, so if I give, I get 0.4177. If I take 0.3545 minus 0.0632, I end up at 0.2913. Okay. So what percentage of people in the US drive trucks? My answer is somewhere between 29% and 41 or 42%. Okay. It's quite a big range, but that's because I've only surveyed 220 people, okay? and not even I just made these numbers up. So, but you know, we're saying, okay, well, what percentage of people drive trucks? Something between 29 and 41%, 42%, something like that. Okay, is that okay? So my answer, okay, is I would say I am 95% confident that the proportion of people who drive trucks is between 0.2913 and 0.4177. And there we go. Does this feel okay? No? Do you want another example? Yeah, okay, we can do another example, just like this, all right? Because you'll see something like this next week. All right. Okay, so yes.
The higher number of people surveyed would increase the margin of error, or
If we, this is a good thing to point out. If we surveyed more people, our n would get bigger, and that's in our denominator. So our margin of error actually shrinks. If we survey more people, like if I surveyed 2,000 people rather than 200 people, 220 people, okay, then I won't have as much give or take. I would say, well, I'm pretty because my 2,000 number based on 2,000 people gives basically more information, or we're more confident in this number. So the amount of give or take I have to use can be smaller. Okay, so instead, right now I'm saying give or take 6%. Okay, if I survey a lot more, I can say, oh, my margin of error is only 2%, something like that. Okay, right? Because if a news organization said, we predict, so and so, has a lead of, 53% to 47% with a margin of error of 6%, you'd say, well, that's not helpful, right? Because we want to know, is this candidate going to win, right? So we don't want 53% with a margin of error of 6%, okay? We want 53% with a margin of error of 2%, or something like that, right? We want something less than 3% as our margin of error. So, so that's what we say, okay? Well, here's another question. So if somebody says, do we have evidence that the percentage of truck drivers, or not truck drivers, people who drive trucks is different from 40%? So some, maybe some magazine says 40% of the population own trucks or drive trucks, okay? Do we have evidence that that magazine is wrong? No, because 40% is in this number, okay? 40% is in between 29% and 41.7%, okay? Basically, these are plausible values for us based on the data we've seen. If, on the other hand, somebody makes a claim and says, I believe the percentage of people who drive trucks is 70%, something like that. Do we have evidence that that guy's wrong?
Yes.
We do. If they say 70%, that's outside of our range of plausible values. So, we'd say, well, I don't think that's right because I surveyed 220 people and I created this confidence interval, or basically this zone of plausibility, and that only goes from 29 to 41%. So I don't know how you're getting that number to 70%, okay? So we can say stuff like that. But any number in between 29 and 41, we just say, yeah, well, you're not necessarily right, but I can't say you're wrong either, okay? So if somebody claims it's 30%, we can say, well, that could be the case. It doesn't prove that 30% is right. It just means, sure, that could be, okay? where, you know, that's the unsatisfying part of statistics, is a lot of times we can't prove someone to be right. Okay, all we can say is they could be right. I have nothing to say that they're wrong. Okay. So we'll try another example here. Okay. Let's see. So here's our values again of z. And I will say, oh, and here's our formula, p hat plus or minus z star okay, so I'm going to write we wish to know what percent or what proportion, we'll just stick with proportions, what proportion of, I don't know, we'll just say people where, we'll say people in, I guess in the US again, wear corrective lenses. Of some kind. Okay, so we have surveyed. We surveyed. We'll say 300 random people. And we will say 165 of them. No, maybe that's too much. That's fine. Okay, 165 of them wear corrective lenses. Okay, now I'll say make 90% confidence interval. For the proportion of all people who wear corrective lenses. All right, so take a few minutes to work through this. All right, looking around, it looks like a lot of you guys were doing pretty well here. Okay, so we have correctly identified p hat as 165 divided by 300. So we have a nice number to work with, 0.55. Okay, which tells us our n is also 300. And because it says 90% confidence, we know our z star is going to be 1.645. So I'm going to just plug in all of these numbers where I have them. So p hat is 0.55 plus or minus z star 1.645 times the square root of p hat 0.55 times 1 minus 0.55 divided by 300. Okay? Now you could punch all of this into your calculator in one go, do the plus side and then go back and do the minus side. That's allowed, okay? I like to kind of break it out into different steps. So I usually do 0.55 plus or minus 1.645, and I try to figure out this part up here first, okay? So I do 0.55 times 1 minus 0.55, close parentheses, divided by 300, and I take the square root of that. You don't have to do it this way, but this is how I do it. And I get 0.0287, okay? Again, I don't feel like retyping all of that in, so I just hit answer, multiply 1.645, and I get 0.0472, okay? So I have 0.55 plus or minus 0.0472. Okay, so now I have to do the typing. 0.55 plus 0.04 0.042. This gives me on the on the high end, or what I might call the upper bound of our confidence interval, is going to be 0.5972, and my lower bound will be what happens if I subtract 0.0472. So I just do the same thing, 0.55 minus 0.0472, and on the lower bound I have 0.5028. Okay? If I were to ask you what is the margin of error, you would tell me the margin of error is 0.0472, right? The give or take part. The part that comes after the plus or minus, that is our margin of error. If I asked you what's the center of our interval?
Wait, how did you get the margin of error?
The margin of error is just the part that comes after the plus or minus. It's the critical value times the standard error. Okay, so the center of the interval is 0.55. I guess I'll just label all of these parts. Our critical value is what? 1.645. And our standard error, these are, all I'm doing is just giving you the names of each of these numbers that you see. Our standard error is the 0.0287. Okay, this is our upper bound, this is our lower bound. And I would write something like, I am 90% confident that the proportion of people who wear corrective lenses is between 0.5028, so basically 50% and 60%, and 59.5972, 60%. So I'm 90% confident that the proportion of people who wear corrective lenses is between 50% and 60%, basically. Or I could say 55%, give or take 5%. Yes?
Where did you get the standard error?
Right here, 0.0287.
And how?
What do you mean? So I multiplied 0.55 times 1 minus 0.55 divided by 300, and I take the square root.
Okay, and from that you get the margin of error.
Correct, yeah. So I'm just, all I'm doing is, you know, look at this thing. I'm just applying labels to these things because when we created confidence intervals, the people said, hey, we're going to call this thing the critical value. We're going to call this thing the standard error, okay? I'm just telling you that these are what they're called. It's not like I said, oh, I'm making up stuff here. No, this is what we have here. Okay, we'll end here. Please, yeah, do your homework and then work on the practice quiz, and we'll see you guys next week. The practice quiz will just cover the stuff we've covered today.